Okay, so y'all are working on it, but I'm just going to go ahead and write these down and make sure you know how to do this. I'll say as I go, for this trapezoid, the rise is 3, the run is 4, so the slope is 3/4. Here, the rise is -6, the run is 4, so we get -3/2. Here, the rise is -2, the run is 4, so the slope is -1/2. And here, the rise is 6 and the run is 4, so the slope is 3/2. Now again, if you can't do that in your head that quickly, two things. One of two things, and probably a combination. One, you're still thinking about how you get a slope too much, okay? Two, you're not used to doing enough mental arithmetic, because there's no mental arithmetic in here in calculating these slopes that involves anything but single-digit numbers, okay? Now, if you need, okay, now the area here, well, you know that if you reconstruct this trapezoid with 7 here and 10 here, you're going to divide this at the midpoint, you're going to get a rectangle whose altitude is 10 plus 7 over 2, the average of these two altitudes, which is 17/2. Okay? Right? If I did that right, because, you know, my mental arithmetic. Yeah. Okay, so, and I'll label these in green so they don't get confused with the numbers I've already got here, because this is kind of small. Okay? So I'm going to put this area here. Well, now you then have a rectangle 17/2 by 4. 17/2 times 4 you should be able to do instantly. You know, 2 divides 4, 2. 2 times 17 is 34, right? So you get an area of 34, which I'll circle. That's a little small to read. I didn't know some of you were going to hide in the corner, but you understand what I'm doing. Okay? So similarly, okay, here, 6 and 10, you know, you're going to get the average, and the average of, I'm sorry, it's not 6 and 10, it's 10 and 4. And the average of 10 and 4, you should instantly see to be 7. Again, if you're relying on a calculator to do such things, try to start avoiding that. And here, 4 and 2 average out to 3, and 3 times 4 is 12. Got to write that small because I need to write something else in there. The average of 2 and 8, you know, is 5, and you multiply that by 4, and you get 20. So the numbers are 34, 28, 12, and 20. You got to write those down. Okay? So we get that. Everybody gets that. Now, there are two other things that we want to label. One we call the rate of slope change. Okay? So we'll just kind of draw. I want to leave myself enough room here, and I just didn't. Okay, I'm going to sketch these slope segments here. Okay, so I've got 3/4 and -3/2. Those are my first two slopes, right? Okay? Okay? What's the change in the slope as I go from here to here? I mean, just tell me. You don't have to give me a fraction. Just tell me what two numbers I'm going to use and how I'm going to use them.
3/4 to 7/2.
Okay, we go from 3/4 to -3/2, right? So what number am I going to associate with the change as I go from 3/4 to -3/2?
3/4 to -3/2.
Again?
3/4 to -3/2. You would just use those two numbers to find the change.
Okay, you said 3/4 and -3/2. Well, those are the numbers I'm going to use. What operation would I use? Again? So if I add these, well, like, okay. If I go from milepost 12 to milepost 4, what's the change?
8.
The change is -8. That's important. Now, what operation would I use to calculate that?
12 minus 4.
Subtract.
So 3
No, I
fourths.
don't do 12 minus 4. If I do 12 minus 4, I don't get -8.
4 minus 12.
4 minus 12. I take where I end up and subtract where I started. That's how I get the change.
So
If you got two temperatures and you want to see how much the temperature changes, what do? Do you subtract the original temperature from the final one or the final one from the original?
final conversion.
And we talked about that a few days ago, but y'all didn't pick it up well enough, okay? So make sure you lock it in now. To get the change in a quantity, you subtract the original from the final. Because that's the only operation that makes sense in terms of a temperature change. Okay? You got to know in what direction the change goes, up or down. And when you take a change in a vector, you got to know the direction, and the vector might have 2 or 3 components or more. Okay? So you got to have this down before you can understand what a change is, and how can you do calculus if you don't understand what a change is? Well, you can do a lot of calculus. You can learn how to do the operations. You can learn how to manipulate the quantities, but do you really totally understand it? Well, to totally understand it, it's like drilling for the core of the earth. You're never going to get there with any technology we have. And you're never going to get to the total depth of the mathematics or the physics or anything with what the equipment you have, namely a human brain. Most of you have human brains, am I correct?
No, mine's alien. I'm an expert.
And even artificial intelligence will never get there. Not with anything that has any real depth, okay? There's no end, there's no limit. So my point is, you start with a simple idea and make sure you got those simple ideas so that you understand things more deeply, okay? There's a calculus text that I would have loved to work through with my grandson while he was here, okay? And it's a calculus text. In Europe, a lot of people use it. Swakowski's calculus. Oh, no, it's Spiegler? It's not Swakowski. I forget who it is, but I got a copy so I can find out. I can do the problems, but most of them challenge me. And I know, calculus is the first thing I took in college. I went 7 years studying deeper and deeper mathematics. But just in calculus, there's depth that you can't get to. And in the book I'm working through, not this week because I spent all my time on this, but the week I'm working through, or the art of computer programming. I said those problems go from 0 to 50, and the 50s are research problems nobody's ever solved. Okay? The ideas are simple. The idea is that you understand if you've had your typical first couple of years of a rigorous engineering, physics, hard science curriculum. But applying them and solving the problems is a mess. And the problems you're going to have for the final are kind of core of the earth problems, see how close you can get. Although you can solve these problems. But once you've solved them, they raise different questions and go deeper. Now, if you can go to the depth of what I've got on this piece of paper here, on every problem, that's kind of an A plus 4. That'd be an A and 4 pluses, okay? And a lot better than the D minus, right? And, you know, default grade in this course is a D minus if nobody wins a Nobel Prize by next week.
Huh?
I very seldom had to give anybody a D minus. Majority of people do,
Make
Make-
A's.
probably, but it's just a majority.
That's not reassuring.
In most years, I don't have to give more than one C. In many years, I don't have to give any.
How do you grade the class?
This class.
I take the papers to the top of my stairs and toss them. Whichever ones go further have more ink on them, so you tried harder, so you get the higher grade.
Really?
No.
Bet.
I was gonna say, I'll make mine so that we can do it.
I evaluate the quality and depth of your work. And I get it right. And then I compare. If I've got these people make A's, these people make B's, and hopefully nobody makes any lower than that, okay? So let's just say I've got all A's and B's. Then I take every A and compare it with every B and say, is this really better than this? Okay? Usually there's a pretty clear line of demarcation, but if it's close, and if I can't decide, if there's a B, then I can't decide that it's better, whether it's better or worse than this A here, gets the A. Okay? So it's a comparison process. First of all, I grade them, say, here's what I think. Then I make comparisons to make sure that I was in, not, you know, maybe I was in a different mood when I graded this one and came out 2 points lower.
So
Okay?
can I ask a question?
If it's a 2-point difference, I question the heck out of myself. And I don't lower the A, I'll raise the B. Okay, if I decide this is worth an A, then that's worth an A. Every A I give is worth an A, and then I see if any of the B's are really worth an A. And to see if anybody's, you know, okay, and if there's a big gap in the B's and it goes down to this, you know, put points on it. If the average, if B's run from 55% to 77%, which might be because it's a hard test, right? Or a score of 55 to 77, okay? And somebody has a 32, they're probably not going to get a B, right? Make sense?
What if we all do close to the same?
If they all come out the same, everybody gets an A.
How do we check our grade?
So if we all
Huh?
fail,
How do we check our grade?
we all get an A.
You can email me, because by the early part of that weekend, I'll know. Usually, I can tell you on Monday, because usually we take all day Monday for the final.
I thought we finished Friday.
Monday, I'm talking about like next Monday. So normally the final would be the day we're leaving for our 3-day trip, okay? So, you know, by the end of the day, you know, people, you know, the way I usually run it is I have a pile of problems and I'll hand out problems one at a time. You finish a problem, you bring it to me, I give you another one. And I grade that one pretty much immediately unless it gets really intense and I don't have time to get behind. So by the end of the day, I go over into that room, which is usually empty, and say, come on over one at a time, I'll tell you how you did. I can't do that. And I won't be able to do that Friday because Friday morning is part of the final. And then we have the graduation and everybody disappears and I won't have time to do the grading. Now I might, yeah, and then I won't have time because your take-home final won't be due till the morning. I just won't have time to make those decisions on Friday. Yeah.
How many questions are going to be on the final, on the 3-hour final?
I don't know yet. I don't know what the questions are going to be. I've got a rough draft of things that I would like to get to, okay? And I'll be able to give you a better idea on Friday
So we
when I'll either have or be ready to post the take-home. And then I'll probably be thinking throughout the trip about just what I want to put and how I want to do the in-class final. So I don't know how many questions there are going to be, but you can count and staying busy for 3 hours because I'll have more questions than anybody can do.
So what if we don't finish though?
You won't finish it.
So then we get a bad grade?
Just like, you know, I'm not going to do the 50-level problems in the art of computer programming. Nobody's ever been able to solve them. You know, if I had a few extra hours, of course, I'd be able to solve any of them, but, right. You know, I'll be lucky to solve some 30s, okay? Because, you know, working memory's not what it was. And the 40s, as he says, are good problems that you assign to a good graduate student for a semester-long project, okay?
So
You know,
40
I don't have that much time left in my life, okay?
So-
I'm not going to devote 3 months to one of those problems unless it really interests me,
So the 40s,
because I have other things to do. Huh?
the 40s would be like a problem that would take all year long.
Could be. Could be.
How would it take all year?
Because you got to keep thinking about it every day. Or think about it for a week, put it away for a week, and hope something clicks. Then come back to it and keep preparing and waiting for things to click. That's how research mathematics works. That's how any subject, any topic at a high level works. Okay? So, you know, I've solved some. You know, one day my professor came in to topology class and said, I can't solve this problem. So several of us went up to the board and embarrassed the heck out of ourselves by thinking we had a solution and didn't. It's a homework problem, including one guy who was probably one of the top 10 undergraduates in the country at the time.
What's an undergrad?
So I was a little embarrassed, and that's usually what motivates me. So I thought about that problem all day. I had some other homework to do, did it, and thought about it most of the next day, and that night it clicked. And I went in and said, okay, I think I've got a solution. He said, come to my office afterwards. Went to his office afterwards. He, Korean guy, and his formerly intimidating Chinese buddy. It's intimidating not because he wasn't a bad guy, because he was really smart and really good professor. And this guy that was in the top 10, I think, nationally, as an undergraduate. Went over to his office, and I spent 2.5 hours convincing these guys that I had a proof. Okay? You know, you get problems like that, and that was my first semester of graduate school. Okay? And then, you know, the guy said, this Chinese guy said, something to the effect that, yeah, you convinced us. That wasn't a very elegant proof, but it was a proof. And
So
that's
you
very
did
good.
solve it.
Huh?
So you did solve it.
Yeah, I solved it. At least I convinced those guys that I'd solved it, and I knew I'd solved it. You know, I was real confident. So, yeah, but I'm arguing these 3 guys down for 2.5 hours. Okay? And one of the few really good things I did as a graduate student. Okay? Because when it came time, when some guy who was really smart dropped out of graduate school, and I just happened to be walking by when he was talking to the guy and saying he's getting married and had to drop out, they asked around, what are we going to do with this guy's fellowship? And this Korean guy and this Chinese guy piped up and said, give it to this guy. I got it. Then they figured I was an idiot a couple of years longer, so I just left. Okay. You know,
Wait, so
I didn't plan to go to a PhD. It would have taken me an extra 4 years. I had the master's degree, and that was good enough. Because I knew that I was not going to be a profound researcher. I knew I could do research. I'd done a little bit. I knew I could solve hard problems, but not those 50s. Okay? I knew that I could probably do the equivalent of what would be one of the 40s if I had enough time. Now, the point of that story is that, you know, I'm kind of smart, but not smart enough to be a really good research mathematician. Okay? So, you know, I never thought I was. But once in a while I'd solve a good problem, and it was always by a process of immersing myself and then stepping back. Also, when I was in graduate school, I spent at least 2 hours in the gym every day to keep myself sane. Did hundreds of pull-ups and push-ups and played some basketball and, you know, climbed ropes and, you know, did that stuff. And it ran, you know, swam a lot. It took the pressure off, kept me sane, okay? And allowed me to really focus on what I was doing. You can overdo, you know, if you spend 100 hours in your mathematics a week, you might not be as creative as you would if you spent 50, okay? And of course, if that's all you do, if you're a research mathematician, you teach a class or two once in a while, if you're a top level, okay? So my point for you is, they're hard problems and they're worth attempting to solve because it stretches you. You grow a bigger brain. It's like going to the gym and doing something you'd never done before. You get stronger, okay? And worth doing. Now, I'm not going to ask you questions at that level, but again, on your final, these questions are going to be deep questions that theoretically you should be able to drill all the way down to. Not so deep that there's no end to the depth. The questions that could then be expanded a little bit to where the depth goes greater and there's no limit, okay? And the word limit, I don't mean a mathematical limit because that's part of this. Remember yesterday we saw how if you keep subdividing the partitions of a trapezoidal graph, the area approaches the area under the actual curve, right? Because the trapezoidal sections get really close to the actual curve. So the area has to approach. Now that's intuitive. You have to do more than we can talk about to put it in rigorous mathematical terms, but if you understand that, and then if you get those rigorous mathematical terms, you'll know how to handle it. So, okay? So, as I say, I'll give you questions in this, but okay, so that was a big digression, but worth knowing.